Hello, my name is Paula Bosca, and when this live lecture actually occurred, due to some technical difficulties in recording it, the beginning portion of it did not record. So I'm just, this is recorded at a later date, if you notice a little shift later in the video. Okay. Hi. Well, thank you all for coming. My name is Paula Bosca, and today I'll be talking about space, students, and SBX, the power of curiosity. This is part of McMaster NEUDOSE's Space from Your Place live lecture series. Perfect. So just a little bit of etiquette during the presentation. We'd prefer if everyone keep their microphones muted. Any questions you have can be tossed in the chat, and I'll do my best to answer them at the end. And preferably keeping the discussion to a minimum in the chat during the presentation. Thank you. So with that, space, students, and SBX, the power of curiosity. So first, a little bit about me. My name is Paula Bosca. I am in my third year of the Integrated Science program at McMaster University, and I'm concentrating in physics. I'm the Command and Data Handling Team Lead of McMaster NEUDOSE, as well as the project lead for the High Altitude Balloon mission. I don't know how to write bios, so I subscribe to too many email newsletters, and I have over 1,000 unread emails. I occasionally paint and hope to own a dog or a cat someday. A bit about today, so where it all started, for me at least, I'll talk about first, and then a little bit about why we should even care about space. And then I'd like to tell you all a little bit about the atmosphere, which I like to consider the space that's closest to home, NEUDOSE and SBX, and the opportunities available to students, and then finally the importance of asking questions that you care about. And hopefully lots of pretty pictures in the meantime, like the one on the right here serves no other informative purpose than to look really cool. It's, for those of you wondering, it is a Soyuz liftoff that occurred a couple of days before this live lecture and brought the newest expedition of astronauts to the International Space Station. So where it all started for me and my start with space and why I love space. So it all started with a grade 6 science project on astronomy, and in researching in grade 6, I came across a lot of photos that looked like this, where it showed to scale the size of the planets in our solar system. And it blew my mind because we can barely comprehend the size of the Earth in our everyday lives. When you see photos like that of Jupiter to scale to the Earth, it's insane. But even more mind-boggling, really, was a lot of photos like these were followed up with things like this, where Jupiter is so much smaller than the sun, and then you see in this photo the sun is one tiny little pixel on this screen compared to the size of other stars that we know about in either our galaxy or other galaxies. And it's just it's so hard to wrap your mind around that something so much more massive than us, than our Earth, than our star even exist. And not only that, but even bigger than those, the scales go even larger to our solar systems around these stars, and then galaxies around solar systems, and then galaxy clusters, and then superclusters, and then so much more. The universe and the cosmos is just absolutely mind-bogglingly huge, and that really sparked my curiosity. But as with a lot of stuff, you know, in grade 6, interests don't last, they kind of come and go, and my love of space kind of really got rekindled with a bout of sleeplessness. So in being unable to sleep, I would click around Wikipedia. I'd Google random things. I'd try to learn, ask questions, and figure out whatever was itching my curiosity at the time. And somehow I came across NASA's website, which is a wealth of resources if anyone's ever been on their website. But I clicked the right link somehow, and I came to a photo that looked like this. Except it wasn't a photo, it was a live stream. And so this actually is a screenshot that I took of the live stream a couple hours before the live lecture series, but it's been going on 24/7, and it's a camera on the International Space Station with a view of the Earth. So it has been live streaming 24/7 for the last at least 5 or 6 years. And in this bout of sleeplessness, I found it fascinating and mesmerizing, and I would turn off all my lights and I'd go to bed just watching the Earth slowly passing by, and it was just, it's beautiful and it was peaceful, and it really reignited that spark and that curiosity for space, because I just thought it was so beautiful and cool. So when you're as interested as I am in space, and when you talk about it as much as I do, you get a lot of questions like, well, why space? You know, we have so many problems here on Earth. We have climate change, we have deforestation, we have all these human-caused problems, and you know, we know more about the moon than we know about the bottom of the ocean. I don't know if that's true or not, but people say it is. And why invest efforts and time and money into space? And my answer to that is comes in 3 parts. The first is, because science is critical for human development. Asking questions is absolutely fundamental to what it means to be human. Curiosity and this asking questions is inherent to every single one of us. And that aspect of asking questions doesn't happen linearly. We don't know everything about a subject before moving on to another. Everyone in the world in ancient times to now didn't go, okay, we need to learn everything about fundamental of our universe, physics, before we can start building up, before we can start asking questions about proteins and viruses and germs and bacteria and health and all these things. That's not how we ask questions, and that's not how science works. It doesn't happen in a linear fashion. Every single one of us has this drive and has this inherent need to ask questions and this curiosity, but it doesn't all happen in the same direction. We each have our own interests and our own curiosities, and we go off in different directions. It isn't this sort of linear path. We don't need to know everything about a subject before asking a different question. And finally, when we do that, when we all go off in these different directions, science doesn't happen in isolation. Disciplines aren't truly separate. We each ask questions, we each go off in these different directions, but what we learn in one little branch isn't isolated and separate from everything else. We communicate, we share, and the knowledge and information and science that we learn will inherently affect everything else. Maybe we don't know how at the time we set out to ask a question. Maybe we can't understand all the repercussions or how it'll apply to all these different fields, but through the ingenuity and creativity of human nature, it will inevitably happen. And so that's really why space, because it's an area of development. It's this huge area of pursuit of curiosity and questions about our universe that I would like answers to, and it will inevitably affect everyone and our lives and all these different disciplines. It will somehow. We might not know how when we first set out to answer some of these questions about the universe, but they will, and that's kind of just inherent. So with that, I today want to talk about our atmosphere, because that's really the space that's closest to us. So you don't have to go super far in the universe to really learn about space. And the idea of space being interdisciplinary and what we learn from space being applied to different disciplines, a great example of that is learning about our atmosphere. So this photo is also a real photograph. It's of the Earth's atmosphere, and it was taken in 2009 as the Space Shuttle Atlantis was docking with the International Space Station. So, a little bit about our atmosphere. In really simple terms, it's composed of lots and lots of different gases. It's really like a jacket for our planet. It protects us in many, many different ways. It keeps the pressure just what we need it to be on the surface. It also keeps the temperature exactly what we need it to be. And with this pressure and temperature coming together, we get liquid water, which is absolutely critical for life. And as I'll kind of talk about towards the end of the presentation, it also protects us from radiation. And space is big and scary, and there's a lot of really harmful things out there, and our atmosphere really does a lot to protect us from it. So when we think about the atmosphere, we kind of just think about this giant amount of gas on top of us and eventually get to space. But there's actually some pretty clear delineations. There's different layers of the atmosphere, and they all have different properties, and it's really quite interesting. So going from the bottom up, you can see on this diagram, on the very bottom level, there's the troposphere, and then let's see if this works. Yeah, troposphere, and then on top of that, there's the stratosphere. On top of that is the mesosphere, and on top of that is the thermosphere, and then even higher exosphere. But that's really where you start getting into space. So really these first three layers are the Earth. And you might think that, you know, this is all just some random delineation that some scientists thought of at some point and we just stuck with it. But looking at this diagram, those different colors you see are actually the different layers of the atmosphere. So their properties are so different that they can be seen just with visible light. So on the very bottom left here, that's the Earth. And then that first orange layer is actually the troposphere, the very bottom layer of the atmosphere. The middle white band is the stratosphere. And then blue and going on to black is the mesosphere and above. And that's the Space Shuttle Endeavour, by the way. So it's not just some things that scientists put on paper. So kind of going through a little bit about each layer. Our very bottom one is the troposphere. And the troposphere is really everything that we know. It has almost all of the water vapor in our entire atmosphere. And because of that, it allows for a lot of things that we know about. So the whole idea that hot air rises and then kind of comes back down in these layers of convection because it rises and then the pressure is a little lower and the temperature cools, so it gets cool, so then it falls again, and then you get these this convection, and all of that sort of manifests itself into the weather and the climate and rain and snow and sunshine and all of that. That's all the troposphere. And this is actually where planes fly also. So it extends about 10 kilometers above us, and really of our day-to-day, if you didn't know anything else, that's probably what you thought our atmosphere would be. There's a lot of it, but moving on to the next one is the stratosphere. And the stratosphere is a pretty big layer. It goes from 10 kilometers to 50 kilometers. And this is actually where things start heating up again. So in the bottom layer, you'd think as you get further from the Earth, the pressure starts getting lower and things start getting colder, and that's true. But like I said before, there's these pretty distinct layers. So when you start getting to the stratosphere, things start heating back up again. And this is because of what's a lot of people call the ozone layer. So if you remember, before it was called climate change, people called it global warming. And there was this whole thing with the holes in the ozone layer, and this ozone layer that surrounds the Earth. Well, there's this molecule called ozone, and it sits at a very specific height above the Earth. And it's really, really good at taking the heat from the sun and re-radiating it. So it's really, really good at radiating this heat, and that's why this layer of the atmosphere is so much hotter than the one below it. And it also isn't just ozone. It's a lot of other really pesky pollutants. So back when they did that whole ban against certain chemicals and things like hairspray or refrigerators like CFCs, that's because those chemicals sit in this layer and they're all really, really good at capturing that heat. And so that's why it's really warm up there. This is also approximately where there's this thing called the Armstrong limit, which is as you get further and further from the ground, the pressure starts dropping. And the Armstrong limit is essentially the limit at which, when you go above that, the pressure is so low that the boiling temperature of water is the internal temperature of your body. So you can't be outside in the above the Armstrong limit without essentially the water inside of you boiling. So you need specific sort of pressure suits in order to stay alive, really. And the stratosphere is pretty big, so it, along with the lower layer, the troposphere, actually has about 99.9% of all of the atmosphere. So all of the gases and the mass and everything in it are basically just those bottom two layers, which is pretty crazy. And it's also, when we think about weather balloons, which I'll talk about more in a little bit, because the pressure after this starts dropping off so much too, this is the maximum height that weather balloons can go up to. So the next layer of the atmosphere is the meteor, and in this diagram it looks like there's a lot of things going on. You've got these meteors and these sprites and the standing rockets, which is really interesting, but I found this really neat article by Discover magazine, and they had this interesting title where they called the mesosphere the ignorosphere, because scientists actually know very, very little about this layer of the atmosphere. And that happens for a couple of reasons. It's really, really hard to study this layer because it's kind of in between where aerodynamics takes over and astrodynamics takes over. So below in the troposphere and the stratosphere, we can fly planes and we can fly weather balloons, but weather balloons pop in the stratosphere. So getting to the layer above can be really, really difficult because flying planes up there is very, very hard. So because of that, we don't actually have a lot of knowledge about what's up there. But what we do know is really cool. So another temperature inversion. So as I mentioned before, the troposphere, again, from the bottom starts getting cooler as you go up, and then you have that ozone layer in the stratosphere that makes everything warm up again. But then as you go up another, it starts getting cooler again, and then it keeps cooling. But what's really interesting here is that you get these really weird weather effects called TLEs, these transient luminous events. And on the top here, both of these are real diagrams, real photographs. That's why they're pretty low quality. It's not your internet connection, it's the photo. The top is of a blue jet, and the bottom is of a red sprite. And there are these really weird phenomena that happen when you get thunderstorms and lightning activity, but rather than going down from the clouds to the ground, it goes up. And due to atmospheric composition, gases, and a lot of other weird things that scientists honestly don't know a lot about, you get these jet streams of blue, and you get these weird streams of red, and some really other weird and funky things that there's a lot more to learn about. And so finally, at the very top layer of the atmosphere, really, we have the thermosphere. And this is really where we get into space. So I mentioned here that that's where the Kármán line is. And the Kármán line is this thing that a Hungarian physicist came up with a couple decades ago, where after doing some clever calculations, it's essentially a line that delineates Earth from space. Below that line, really, when you're flying things, you consider aerodynamics. You consider drag and lift and all these things that you'd consider really when flying a plane or a balloon. But above that line, that's when astrodynamics takes over. That's when you need to consider orbital mechanics and all that kind of interplanetary sort of dynamics. So that's kind of why that's where we start getting really space. This is also, interestingly enough, where a lot of the auroras happen. So the northern lights, the auroras at the North Pole, and also their counterparts at the South Pole, a lot of that actually happens in this very, very high layer of the atmosphere that's essentially space. And again, because above this Kármán line is where you have to consider a lot of orbital mechanics, that's where a lot of satellites sit. So for example, the International Space Station is technically in the thermosphere. And finally, it's hot and cold. It's hot because technically it's so close to the sun that the way we define temperature by being this energy of particles, it's technically 15,000 degrees up there. But because these particles are so spread out, they can't radiate that heat effectively, you would still freeze to death essentially. So you wouldn't feel that heat, but technically by our definitions of temperature, it's incredibly hot. So that's just a fun fact about the thermosphere. And finally, a layer of the atmosphere that I didn't really mention is the ionosphere, because it's not really a defined layer. So I showed you that image at the very beginning where of the space shuttle Endeavour, and in the background you see the orange and then the white and the blue. Those are very distinct layers of the atmosphere. The ionosphere isn't. It's pretty much defined as where all the weird high energy particles end up. So on the right, you can see a really cool image taken in 2018 of the northern lights over Iceland. All that kind of activity. I mentioned earlier that the aurora is in the thermosphere because that's usually where they occur, but this ionosphere kind of spans a bunch of different layers. It just kind of how highly charged the particles are and where they end up. So it's really, you got these absolutely incredible displays that are just beautiful, but they're actually incredibly dangerous because to create such incredible displays, you have to have these really high energy particles, and high energy particles can be extremely dangerous. So what creates these high energy particles? What's up there? Where did they come from? And really there's two main sources for the stuff all the way up there. There's the ones from the sun. So on the right, this is an image of a coronal mass ejection, which is really just a fancy term of the sun spewing out a lot of high energy particles. So the sun it's got this nuclear fusion, and it is constantly radiating outwards light and particles and all this stuff, and that's really, really high energy. So a lot of our high energy and the cool displays we get in the ionosphere comes from the sun, but a decent amount of it also comes from these cosmic rays, which are defined as pretty much things coming not from the sun, but still from space. So out in the vastness of the universe, there's a lot of weird things out there. Sometimes stars at the end of their lives collapse and explode in these supernovae that you can kind of see on the left here. And in that process, they expel tons and tons of high energy particles. And these high energy particles are traveling almost at the speed of light. And these things happened millions of billions of years ago, and then eventually they reach the Earth. So part of the things that's bombarding our atmosphere actually comes from dying stars that are billions and billions and billions and billions of kilometers away. So that's also really, really interesting. And another thing that kind of protects us with the atmosphere and so kind of what's up there in that giant sort of sphere around us is the magnetosphere. So magnetism is comically very ill understood, but it's up there. Our Earth has a kind of acts like a giant bar magnet and has a lot of these magnetic fields around it that because a lot of these particles are charged, they sort of move along, and it kind of moves them away from us so that they don't go straight towards the Earth, so that we're protected both by this magnetosphere that extends really, really far out past us, and then also by our atmosphere that's a little bit closer. So a lot of that kind of comes and can be considered radiation. So all of these high energy particles are really basically radiation. And when we think of radiation,
honestly, it depends what background you come from, but it can either just kind of be any sort of electromagnetic wave, like your microwave in your kitchen. That's technically radiation. But when a lot of people think about radiation, they think of this scary thing that can cause cancer and a lot of negative health effects. And the sun and those cosmic rays that I just explained, that's basically radiation. And because they're so high energy, they can cause a lot of those negative health effects. So learning more about the radiation in space, we can learn more about how to protect ourselves from radiation in space and also radiation back at home on Earth. And so this is kind of a big thing on, there's a ton of radiation out there, and how do we go about mitigating it and protecting ourselves, especially, for example, astronauts on the International Space Station. And the first, in really anything is asking a question. It's figuring out what you don't know. So currently there's a lot of gaps in our knowledge in terms of the actual radiation in space. We don't know, I told you how there's cosmic rays and that there's all these weird things from the sun, but the nitty-gritty details of exactly what that looks like, how high energy those particles are, how fast they're moving, how they interact with human cells, how far, how much of a shield do you need to protect yourself from it? All these questions are still slightly unanswered. So there's lots of details and information we still don't know yet. So in this process of learning and helping ourselves and applying all this cool space knowledge, we first have to figure out what we don't know. And once you know that, you then outline a question. So, okay, we want to figure out, what does the radiation look like in space? And from there, this is essentially outlining the scientific method. You consider, what are your possible answers? So what we do currently know and how you can build off of those, and what specific answers are there to your question. And then finally, you kind of move forward with designing an experiment. And that's honestly probably the most difficult thing of all, because designing an experiment to answer your question specifically and not some other slightly related questions, and controlling for things that you can't necessarily see is very, very difficult. But we're kind of doing it. So with NEUDOSE, so as I mentioned in the beginning of this presentation, and what this live lecture series is being hosted by, it's the Neutron Dosimetry and Exploration CubeSat. So a team at McMaster University, myself included, are building a small satellite to do exactly this. A couple of years ago, a bunch of scientists at McMaster and students identified this question of, what does the radiation in space look like, especially around in the orbits that the International Space Station is going in. But more specifically than that, there's different types of radiation. There's charged particles and then there's neutral particles, and what is the difference and kind of what abundance are they in, and how does that differ along these orbits? And so they identified a gap in our knowledge. They asked that question, and they designed an experiment to answer that question specifically. And so through a lot of determination, caring, and hard work, they submitted a proposal to the Canadian Space Agency and now are building a satellite that's going to be sent into space, which is, in my opinion, incredibly cool, but I'm a little bit biased. But what I really want to highlight is that there's space for students in space. For students and people interested in space, there is absolutely room and opportunity to do things. And so a little bit more on NEUDOSE and experimental design. Prototyping is incredibly important, especially for any experimental design, but especially for space, because space, when you send something up there, it's really hard to fix. It's really high up there. There's a lot of weird, wacky stuff going on, and it's just really, really hard to design and to account for all those questions. So once you ask your question, once you figure out kind of how to design an experiment, once you build it, it's very likely not going to work on the first try. And that's honestly true of most things. And that's kind of why there's that saying, try and try again. And especially with McMaster NEUDOSE, because it's this new question and this new technology, there's going to be a lot of new challenges. And with that, prototyping and constantly designing something, testing it, and then reiterating, redesigning, retesting is incredibly, incredibly important. And this is honestly just a file of a project I worked on showing you that I had many iterations of the exact same thing, changing small tweaks, but very important in the long run, in the long term when you're talking about space. So on this theme of prototyping, the McMaster NEUDOSE team is actually working with SEDS Canada, which is the Students for Exploration and Development of Space. So they're a great resource for helping students who are interested in space reaching those opportunities. And they kind of run this campaign where they pick proposals to go up on a stratospheric balloon. So like I talked about earlier, that stratosphere is that second layer of the atmosphere, and that's where when you send up weather balloons, they pop. So sending things up to that high level is pretty close to what space actually gets like. So when you're designing something for actual space, like we are, with the McMaster NEUDOSE satellite, prototyping in an environment that's pretty close is extremely valuable. And what's really, really cool about this campaign that they do is that any student team at a Canadian university or college can submit a proposal. So any group of friends, interested students can sit down and think up an experiment, ask a question, experiment, send a proposal, and potentially actually design it and have it up on a weather balloon. And that's incredibly, incredibly cool and valuable. So like I said, it all starts with the question. How do you answer your question? How do you create your experiment? And really, it's all possible. It's really just all very, very cool and very possible. And so that's kind of one of the final themes I want to leave you on is the role of students. It's not just the stuff of dreams. I personally was never an entrepreneur. I was never that person that was incredibly creative and innovative. I didn't sit down and think, oh my gosh, what if we did this? That wasn't me. But I was just always someone who asked a lot of questions. I wanted to know more, really. I loved learning. And so with that, we're in the age of information. You hear that said a lot, but what I really like to think of it is that we're in the age of collaboration. So there's so much information out there that one person can't know everything. It's kind of just a fact at this point. But when people know different things and then collaborate, you can do really, really incredible things. And again, you don't have to know, you just have to try. You have to ask those questions, try and collaborate with people, and then you can do really incredible things like send a satellite to space. And one of the most important things about this whole idea is asking questions that you care about, asking questions that you're truly invested in the answer, that you want to know, and that you're willing to put in all that hard work to know the answer to. Because again, science is critical for human development. We all have that need and that drive to ask questions. And it's not just science, it's really everything. It's asking questions. And science doesn't happen linearly, but this asking questions doesn't happen linearly. It's not limited to science, it's not limited to a discipline, because science doesn't happen in isolation, but disciplines aren't in isolation. Everything we know and all of human knowledge isn't one specific topic, and we don't sit with it ourselves. Part of it is communicating and sharing it. So I wanted to leave you on that thought and share with you once again this photo that got me so inspired and interested in space. Hopefully I inspired some of you also. And if nobody has any questions, this at the bottom here is all of the information for McMaster NEUDOSE if anyone wants to learn any more. I additionally am free to reach out to you anytime if you want to know more about anything I talked about. And I do believe that this presentation is being recorded, so it will be uploaded somewhere, which I'm sure will be informed to you through the Instagram/Facebook page. So yeah, thank you everyone for coming, and I hope you have a great rest of your night.